Good morning to one and all. It is a pleasure to present our research work in the International Research Award on Global Awards on Primary Healthcare and Medicare 2021 category of Best Research Award. Now I am going to present our work title Electrochemical Determination of Caffeic Acid in Antioxidant Samples via Facile Synthesis of Carbon Ion Based Active Electrocatalyst. I am Dr. Raja Nehru, Assistant Research Fellow, National Kaohsiung University of Science and Technology, Taiwan. Oh, this is in this picture, I'm showing the highlights of our research. In this work, we worked based on the electrocatalyst carbon and ion-based composite material for caffeic acid sensing application. It's showing the developed sensor showing ultra sensitivity at lower concentration with good linearity, and also the developed sensor showing low LOD and low LOQ for key CA sensor. The recommended sensor also contain high sensitivity, selectivity, and stability. Also, the sensor showing a good practical ability for caffeic acid sensing application. So, why we need to analyze caffeic acid? We know very well that caffeic acid is a well-known antioxidant, and also it helps to prevent oxidation of other molecules and to prevent the free radicals in our body. Here, the caffeic acid have two hydroxyl groups. It beneficial to our body, although it act as an antioxidant, anti-inflammatory, and anti-cancer and antiviral abilities. The phenolic acid intake level is necessary to maintain our body diet, particularly caffeic acid. In recent German National Food Consumption Survey shows that the average intake level of caffeic acid concentration to the 206 mg per day. Here we can see that the picture showing that the mean coffee consumption per day mg per day per person showing high level. So we need to maintain our body, and also we need to take particular amount of caffeic acid per day per human body. So we need to analyze this caffeic acid consumption higher concentration in accurate level. Because of this reason, we are going to analyze and sense the caffeic acid by using different electrocatalysts. In this work, we are going to present our carbon and metal oxide based electrocatalyst for sensing application. Normally, carbon materials have considered as an excellent platform for the preparation of composite materials, and also it acts as a very good material for sensing application, and it gives active electro surface area and unique structures, mechanical and thermal stability, and also outstanding charge transfer characteristics. And these carbon materials usually enhance the catalytic activity when combined the metal oxides and metal sulfides. So it will help to enhance the sensing performance toward the electrochemical sensing application. And also this carbon material helps for other combinations and other applications as well. For example, nano electronics and nanomaterial division and sensor application division, supercapacitor applications and catalysis and other application as well. Here we are going to focus carbon nanotube and functionalized carbon nanotube. Why we need to functionalize? After functionalize the carbon nanotube, active functional group to combine with metal oxide composite, then it showed high electronic ability to sense the sensing display. So because of this reason, we are going to use the carbon material for sensing application. Here we can see the composite formation for sensing application. Here the carbon material, when carbon material combined with the metal oxide, the synergetic effect enhance the sensing performance. This is the strategy of composite material formation for sensing application. In this research work, we prepared functionalized carbon material with alpha sodium ferrite composite, and also we fabricate for electrochemical sensing application. For this, first we take sodium carbonate, sodium peroxide, and iron oxide combinations. Further, it takes handling for 300 degrees Celsius at 2 hours in oxygen gas flow. After completing this step, we further move to solid state reaction for stoichiometric mixture of sodium carbonate and iron oxide in the tubular furnace at 790 degrees Celsius for 24 hours. In the After reaching the 790 degrees Celsius, we take quenching up approach in the normal room temperature. Here, the sodium oxide promote the reaction and single phase to get the single phase sodium ferrite compound at 400 degrees Celsius. Meanwhile, when we reach around 300 degrees Celsius, the beta sodium ferrite we observe, but after finally we will get the alpha phase of sodium ferrite compound. After getting the sodium ferrite compound, further we introduce the functionalized multi-wall carbon nanotube and combine with sodium ferrite for composite formation by using ultrasonication approach at 20 a normal room temperature with 20 minutes of vibration. Finally, we get the composite of functionalized carbon nanotubes and alpha NaFeO2 composite material. Further, after getting this material, we modified the electrode surface. Which electrode surface? Here we are using glassy carbon as a electrode surface. After modifying by using deep coating method, we modified the electrode surface, and further we analyze the caffeic acid sensor. So before that, we need to know what is the sensor. Sensor is nothing but the device detect even or or changes in quantities and provides a corresponding results. And the output usually electrical or an optical signals. Sensors here classified two types. One is physical sensor and chemical sensor. The physical sensor that provides information about the physical property of the system, for example, pressure sensor and temperature sensor, etc. And also chemical sensor is a device that transforms the chemical information ranging from the concentration of specific sample component to total composition analysis into an analytical useful signals. Here in chemical sensor, we classified different classification. For example, optical sensor, electrochemical sensor, and other sensors. Here we are mainly focused on the electrochemical sensor. Why we need to focus electrochemical sensor compared to other techniques? Here, these electrochemical sensors are very compact and fast responses and low detection limit for biomolecules. And this electrochemical sensing approach showing low cost effect and simple operation system. And also the application, we can analyze chemical and biological application and we can use industrial and clinical and food monitoring application and environmental monitoring application. So what is electrochemical sensor? Sensor which transform the electrochemical interaction between analyte and electrode into the useful signal to the useful signal. This showing electrochemical sensor. So this our catalyst, we prepared the layered material of sodium ferrite and the combination of uh, functionalized multi-walled carbon nanotube. Here we can see that the XRD patterns showing the hexagonal hexagonal crystal structure, and the same image showing the layered disk-like structure. And also the figure in this picture, figure E shows that the combination of functionalized multiple carbon nanotube and sodium alpha based sodium ferrite. This composition confirms the elemental analysis and EDOX analysis. Here we can see the confirmation sodium presence and uh, iron, oxygen, and carbon presence. Here we can confirm that the composite formation is successfully analyzed through SEM and XRD analysis. Here we can see that in this picture, we can see that the multiple functionalized multiple carbon nanotubes and sodium ferrite disk-like structures, and also this composite showing the d spacing around 0.247. And also we analyze the presence of mixed individual elements of iron sodium ferrite. Here we can confirms that iron presence, oxygen, and sodium in the temp mapping analysis. Also, we observe the functional groups of FTIR analysis. Here we can see that the functional groups are around 3,400 is assigned to the Hogarth trusting vibration mode on the hydroxyl group, and also the 1,500 attribute the stretching bond of C double bond C, and and the, here we can see that the combination of presence of iron and oxygen stretching vibration, I, which confirms the uh, alpha iron oxide. Further, we analyze the beta isotherm for the calculate the surface area. Here, the figure A shows the functionalized multi-walled carbon nanotube bed surface showing around 123.14, and a sodium ferrite showing 1.70. After composite formation, it's showing around 5.50 there. So it can confirm the when we introduce the carbon material to the metal oxide, it enhances the surface area, which helps to detect the heavy acid effectively and show the sensing display effectively. And also we analyze the XPS spectrum of the catalyst. Here we can confirm the survey spectrum showing the presence of carbon, oxygen, and iron, sodium. Here also we confirm the figure B shows the Fe2P peak, and C shows the oxygen O1s spectrum, and D shows the C1s spectrum. Here we confirm that ONS spectrum, in this ONS spectrum, the alpha ferrite and sodium oxygen combination bond formation, and C1s spectrum shows the carbon presence C double bond C and the C single bond O, and carbon ion uh, compound presence in the binding energy level. So further we analyze the cyclic voltammetry study for electroactive surface area to calculate the electroactive surface area, and also we have from this analysis we take ferricyanide system to analyze the electroactive surface area for the different electrodes. For here we use the bare GCE and other composites showing active peak to peak after composite material, the peak to peak separation is low compared to the bare GC electrode, and also showing the electroactive surface area is high compared to the bare GCE. Here we can see that the electrochemical behavior of caffeic acid after without the presence of caffeic acid, there is no signal observed, and the composite material showing the peak responses background is high capacity, and also after the presence of caffeic acid, we show the accurate and sharp redox peak we observed with high peak current responses. We can see the after composite formation, the peak current is enhanced around 32.88 in the redox current responses for a different electrode study. And also here we observed the pH medium 3 and pH 5 and pH 7, 9, 11 in the phosphate buffer medium. It's showing pH 7 is showing high peak current responses and sharp caffeic acid sensing display. You can see the current responses and potential differences. Here we observe different concentration of caffeic acid, and here the concentration is the scan rate is constant and the concentration is different and showing the linear responses. And also we further analyze the scan rate study, it's showing the linear responses. Here we can see that this is the possible mechanism of caffeic acid sensor. Here in this pH study, the pro in this pH study, pH 7 showing high sensing display with peak current, good peak current, indicating the 2 electron to proton transfer. Here in this R1 reaction followed by deprotonation, and also in contrast, the peak current of caffeic acid decreased after excited after reach the pH 7 medium, which were related to the small number of protons takes place in the electrooxidation of caffeic acid at the pH 9 to 11 medium in the GC electrode modified GC electrode surfaces. From this observation, the oxidation of caffeic acid becomes unstable and irreversible homogeneous chemical reaction in higher pH medium, which shows the chemical reaction of mechanism of R2. Finally, we analyze the analytical performance of caffeic acid detection by using differential pulse voltammetry technique. Before we analyze the cyclic voltammetric technique, now we confirm the accurate level of caffeic acid detection by DPV method, because compared to CV method, DPV method is too accurate, and also compared to the IT prometric technique, DPV is showing good response for caffeic acid detection. Here we can see figure B shows two linearity peak, which is showing the around R square value 0.99, and the second linearity showing 0.98. Here the lower concentration level showing high sensitivity up to 17.2 micromolar. After reaching the 17.2 micromolar of caffeic acid in the surface of electrocatalyst, no active surface area have no active surface area in the electrode and electrolyte medium. So after increasing the concentration 17 to 17.2 micromolar to 154.7 micromolar, the sensitivity showing low compared to the low concentration. It's showing 3.89 microampere. And so this sensing performance showing low LOD and low Q. Further, we need to confirm the interference when we introduce the other biomolecules or other acids into the caffeic acid medium. The interference ability we need to study. For that, we analyze the interference with the help of caffeic acid, ascorbic acid, uric acid, and hydroquinone, and gallic acid, and citric acid. Here we can see the below the 5% of error we observed, which can shows that the anti-interference ability is too good for this proposed sensor application. And also the cycle stability, we perform around 50 cycles for the after addition of caffeic acid. It's showing after reaching the under 50 cycles, 79.51 percentage initial current we observed. This is the comparison table for the previous literature and our proposed electrode showing good detection limit and good peak responses for caffeic acid detection while comparing to the previous literature. Finally, we observed the caffeic acid performance by using for electrocatalyst with different caffeine medium, different caffeine sample like coffee and green tea and grapes medium, so to analyze the caffeine performance. Here we can see that after raw sample inject into the electrolyte medium, we observed good sensing display we observed in these three real samples. So here we can confirm that our proposed sensor showing good sensing ability towards the caffeic acid sensing performance. In conclusion, our proposed sensor showing successfully prepared by simple ultrasonication method, and this synergetic effect perform improve the incorporation of conductive functionalized multi-wall carbon nanotube and sodium ferrite, and also the developed sensor achieve the ultra sensitivity at lower concentration level, and also our electrocatalyst achieve low LOD and low LOK, and also the recommended sensor contains high sensitivity, selectivity, and stability. Finally, the recommended sensor showing good practical ability towards the detection of caffeic acid sensor. Finally, I would like to thank the organizing committee members and NKAST and other organizing members for the wonderful opportunity to present our work in the Global Healthcare Award. Thank you so much.